Hi, welcome to this video presentation. In this video, we will talk about the weights used by a simple recurrent neural network. We will take a very trivial example to go through the two types of weights, differentiating the RNN from standard neural network. RNN handles the data in a slightly different manner, which is sequential in nature. So the weights used in these RNN networks are also different than traditional neural network. Essentially, RNN cells needs to process two things. One is the input, which is the current input vector. It can be a number scalar or it can be embedding. Like input vector being embedding can be pushed to the RNN cell in terms of the n-dimensional vector, and also it needs to process the previous previous summary, or rather summarized view of the previous input, and that's called the hidden state. Pretty much like this. So it has to handle two inputs. One is the current input, the other one is the previous, you can say previous input, or the summarized value of the previous activations. Now, these two things will require specific weights for the input and also for the hidden state or the activations from the previous step. So two sets of weights are required, one for the input side, that means the current vector, the input token vector, and this is the set of weights that you need. One is called weight, the other one is called bias, and this is used, both of these are used to transform the input features, namely the embeddings. And essentially, this means how much each feature of the current world is really useful for the model, and determine how much each component of the input vector contributes to the overall, or rather the new memory or the hidden state that it has to compute. The shape of the weight matrix here will be the shape of the hidden size. For example, in this illustration, we have a hidden size of dimension 1, and the dimension of the input vector is 4. So the shape of the weight matrix is going to be 1 times 4, or one row of 4 columns. For example, here 0 0.2, 0 0.1, 0 minus 0.4, and 0.3. So that is the weight matrix, which is going to be used for converting the input embedding into a linear transformation. So if the input vector is 4 dimension and the hidden is 1 dimension, the shape of that will be 1 cross 4. For each time step, the RNN computes the dot product of the input and the weights, uh, essentially the weighted sum of it. So that's one side of your weight matrix. And the corresponding to the input, we also need to have the bias. So bias is defined here as part of the weight and the bias pair. And the purpose of the bias is same as that we saw in the linear regression as well. Essentially to allow the model to shift or adjust the influence of the input on the output. And that is precisely what the linear regression also does. So here the hidden state size, the shape of the bias is simply the hidden state side, which is in this illustration, the hidden state is going to be 1 dimension, or rather scalar value. So the bias is also going to be that shape, and we simply use the bias, or we rather add the bias to the linear transformation of the previous step, and before activation and after activation, the output of the W and the bias matrices will go to a activation function in ReLU, or can be tanh. Now, the next pair of weight and a bias matrix is going to be recurrent weights and a bias. That means we also have to maintain the weight matrix or bias matrix for the hidden state. And that would be another pair here. So the recurrent weights, WH, is used to multiply the hidden state. And these weights connect to the previous hidden state, and they're multiplied with the memory, from the last time that carries the historical information into the current step. So that's the recurrent weight, and also you have recurrent bias for the hidden state, and that is the same purpose like a bias for the input value. In many implementations, this can be a single bias vector, and some of the implementations can use different or explicitly different bias for the input and the bias for the hidden state. So that's a pair of weight matrices that we use in the recurrent neural network. In the next video, we'll see how these matrices are used to build, or rather, how the RNN processes these weights to build the memory across the time step. See you in the next video.